Okay guys, let's take a look at today's lesson. So day 2 of our integration unit, let's talk about what we have learned already. And then actually it would be a good idea if you had one piece of paper where you kept all of the integration strategies, the integral strategies that we're going to be using, because we're going to learn a lot of them, a lot of integration strategies, and you will be, have a problem, an integral problem to solve. And it would be a good idea to be able to look at the list of things that you can do, because it's not going to tell you, I'm not going to tell you what strategy to use. So it would just be a good idea to have them in one place rather than, again, flipping through a bunch of notes. So the very first strategies that we learned just a couple of days ago was using the formula. Right? We learned that you can integrate by just formulas. So that would be our first strategy, is using a formula. The second strategy we're going to learn today, and that is called U-Substitution, or U-Sub for short. We're going to learn U-Substitution today, and this would be the second strategy for integration. So let's talk about what you have to be able to use it. Basically, you have to have a function and its derivative present in the integrand. So the integrand is this part right here, which my the cartoon on my syllabus had to do with that, and I know we haven't gotten a lot of vocab in yet, but that's the integrand. The integrand needs to have a function and its derivative embedded in it. It needs to be like multiplication or something. It can't be addition. And if that isn't present, then we can't use U-Substitution. U-Substitution does not work on everything, only some things. And so in order for it to work, we need to have a function and its derivative present inside of the integrand. And we're going to do some examples, and I'll explain how that works. So the first thing that we need to do is choose what we want U to be, which I have found is probably the most difficult thing for students to do. Once you can figure out what U is, normally you're on a roll. But trying to decide what to make U can be very difficult. Just know that if you choose wrong, you'll be able to figure it out pretty quickly, and you just pick something else. It's okay if you choose wrong. What you'll do is you'll choose it, and then you'll take the derivative of it. Notice how this format is the way it looked when we did differentials, with the dx over here. That's the format of the way that the derivative needs to look. So we're going to basically talk through what our choices are for U and why we would choose one over another. So let's take a look at our first example. We have some options here on what we could make U. I could make cosine U, but I don't have the derivative of cosine, right? Sine's not there, so that's not really a good choice, so we won't pick that. I could make x cubed U, but the derivative of x cubed is 3x squared. I don't have an x squared in there, so that's not a good choice. Or I could make this U, x to the fourth plus 2, and the derivative of x to the fourth is 4x cubed, and I do have an x cubed here. Now, don't get really upset or bent out of shape about the constants. The constants aren't an issue. We will deal with them. What we want to make sure is that we have the variable part there. Do I have an x cubed there? Yes. So that's how I'm going to choose my U. So I'm going to choose this for U. So U is going to equal x to the fourth plus 2. What I will immediately do then is I'm going to take the derivative of it. So du equals 4x cubed dx. In order for this technique to work, I have to be able to take every single thing with an x on it out and put only u's in. That's the way U-Substitution works. Everything with x's has to come out, u's would go in. So I look at this, and I don't have a 4 in here. So what I'm going to do is I'm going to divide the 4 over, and I'm going to have 1/4 du equals x cubed dx. This is my work for my U-Substitution. So now let's compare it to the actual integral. So this part right here is this part. It's going to come out. What I like to do is here on the right side are the things that are coming out of the integral. And here on the left side are the things going into the integral. That just really helps me. It's a much cleaner substitution. There are other ways to do it, but this is just the way that I prefer. So that's why I'm teaching this way to you. So that's what I would do. So here, I know that's coming out. All right, and it's going to be replaced with a u. Then we have this piece right here, x cubed dx, the x cubed and the dx. It's coming out, and it's going to be replaced with 1/4 du. Now, do I have anything left in my integrand that has x's with it? No, I have taken care of all of them, and we have to. Now, before I rewrite this, I need to address something that has caused problems all day long, and that's this little dx guy, or the du guy, whichever form you're in. Let's talk about it. What did we say it was used for? It was used to tell us which variable to integrate. So it's a command. Integrate with respect to x. Once I have integrated, what happens to it? It's gone, right? I don't need it anymore. If you recall from the daily work, once you integrated, did you have a dx left over? No. And that has been troubling students all day for some reason. They're like, where did the dx go, or where did the du go? I'm like, well, we integrated. We did what it said to do. Now it's gone. Okay? It's not like a variable that you integrate. It's a command. It's telling you what to do. So, are we okay with that? Okay. So let's rewrite. I'm going to rewrite this. I would prefer, so again, this side is what's going in. This side's coming out. And so I would prefer to put the 1/4 out here. Again, that has troubled students all day long. It's okay. You know, it's one of the 2 integration rules I have. I can put constants outside, and I can, split it up by addition and subtraction. That's all I got, so I'm going to use it. It's just cleaner. It's a cleaner integration for me. So I just put the 1/4 outside. Then I have cosine u du. So look at the complexity level of what we're left with. Whatever we're left with needs to be a formula that you know. If it's not, then you picked the wrong substitution. Do we know an integration formula for cosine? Yes, and that's what we're going to use. So now we do the integration with cosine. So again, we think, what would I have taken the derivative of to get cosine as my answer? Sine. So my answer is 1/4 sine u plus c. My very last step is to take the u out. Right? I'm not allowed to leave it in there. Because did they ask us to solve something with the u in it? No, that was our choice. We switched it out for our ease of integration. So now we put the u back in. So my answer is 1/4 sine x to the 4th plus 2 plus c. And that is our very first U-substitution problem. How are we doing? We're okay? Pretty good? Okay. I have a few more on the next slide that we need to go to. Does anybody still need this? Okay. So the way that you will know that you have chosen incorrectly for u is when you get here to the substitution part, you're going to have something left that you don't want. Or you're going to end up with something you don't know how to integrate. Right? That's going to be one of those 2 problems. Either you don't know how to integrate it because you don't have a formula for it. Integration is very specific. You have to have formulas for everything. Or there's an x left over or something. Okay? All right, so we good? All right, let's go on to our next slide. All right, so let's take a look at the first one up here. Let's look at our options. I could make x u. What's the derivative of x? 1. Is that really going to help me with that denominator? No, not really. I could make the whole denominator u. But if I do that, it's a radical. Doesn't a derivative of a radical give me another radical? Okay, that's not a good idea, right? I don't have 2 radicals to deal with, so that's not a good idea. So my other option would be just the stuff under the radical. just make this part u. And that would work, right? Because the derivative of constant is 0 and the derivative of x squared is a version of x. So let's do that. Let's make u 1 minus 4x squared. That means du equals negative 8x dx. I don't have a negative 8 in there to pull out, so I want to move it to the other side. So I'm going to divide by negative 8. So negative 1/8 du equals x dx. And there's my U-substitution work. All right, let's see if we're prepped and ready to go. All right, so the x dx is this part right here. That part's coming out. Then we have the 1 minus 4x squared. That part's coming out. So is there anything left to worry with? There's no x's left. So we made the proper choice. This is going to be a good choice. So we rewrite integral. So instead of x dx, I'm going to put negative 1/8 du. And then in the denominator, I have square root of u. Now I know that's very troubling the way that looks. So I will rewrite it. So it won't, some students are very troubled by this. It's okay. You can leave it like this. Another way to write this exact same thing. So u, the 1 over u squared is the same thing as u to the negative 1. 1/2, right? So u to the negative 1/2 du. Some people would like it written better like that, but it's the same thing. We recognize that it's the same thing. So let's integrate. So the antiderivative of u to the negative 1/2, we use the reversal power rule. So we add 1 to negative 1/2 and get 1/2. Then divide by 1/2, which is multiplying by 2. U to the 1/2 plus c. So then we clean it up and put the u back in. So I have negative 1/4 square root of 1 minus 4x squared plus c. And there's our second U-substitution problem. How are we with that one? It's okay? Now, one thing we've got to keep in mind, and I'm going to talk about it in regards to this problem, really important concept. I can pick anything for u. I do not have restrictions on that. I can pick stuff in the denominator or maybe an exponent. I mean, I can pick u to be anything. But the derivative itself has to be exact. So, for example, I needed an x here. What would have happened if this x had been down here? Would I really have an x? No, I would have had a 1 over x, and that is not going to work. The derivative itself has to be there in the exact form. Does that make sense? And I'll show you as we work some problems where we're not going to have a choice because of that problem. By doing my reversal power rule, adding 1 to this, and I get 1/2. So I divide by 1/2, which is multiplying by 2. Okay? All right, so let's move to our next one. So my choices are, I could make cosine u. If I make cosine u, the derivative of cosine is negative sine, but how many sines do I have there? I have 3 of them. And that's not going to give me 3 of them, right? So that is the wrong choice. I can't make cosine u. Does that make sense? Because I have 3 sines to deal with. Instead, I need to make sine u. All right, so let's do that. So u equals sine x, du equals what? Cosine x dx. So let's do our checking. So the cosine x dx is coming out. That's going to be replaced with du. And then the sine is coming out. That's going to be replaced with u. Okay, did I take care of everything that had an x in it? Yes. So I rewrite it, u cubed du. And the rule that we would use here would be the reversal power rule, right? Isn't that much nicer looking than what we started with? Yeah. So reversal power rule, we get add 1 to 3 and get 4. So that's 1/4 u to the 4th plus c. And then my last step is to put the u back in. So it is 1/4 sine 4x plus c. That's a plus. Okay? Are we getting the hang of it? It's not too bad. The next one, tangent. I don't really have any U-sub working here yet, but if I made it, use the quotient rule, that would be probably good, right? Quotient rule for tangent. Yes, trig is still with us and doing well. Quotient rule for tangent would be sine over cosine. Now, it looks like I could pick either one, but that is not the case. Now, we know the derivative of sine is cosine, derivative of cosine is negative sine, but I can't pick just either one. So let's talk about, what if I picked sine to be u? What's the derivative of sine? Cosine. Do I have a cosine there? No, I have a 1 over cosine there, which is really secant. I have secant there. I don't have cosine. I cannot choose sine to be u. You with me? Because the derivative really does, it appears that it's there, but it's really not. It's 1 over cosine that's there. So I don't have a choice. I have to pick cosine. I have to pick cosine to be u. So u equals cosine x, du equals negative sine x dx. I don't have a negative in here, so I'd move it over. Negative du equals sine x dx. Okay? So again, this side, the right side is what's coming out of the integral. The left side is what's going in. So let's rewrite. So the cosine is coming out, and it's going to be replaced with a u. Negative is out here. Sine x dx is coming out, and it's going to be replaced with a du. Now that, the way I wrote that would disturb some students, so I'll rewrite it a different way. It's the same as this. Those are identical. So do we recognize what that is the derivative of? Natural log of x, right, or u, natural log u. So my integral is negative ln absolute value u plus c. And my very last step would be to put my u back in. Negative ln cosine x plus c. Okay, we doing okay? Excellent. One more problem. Okay, what does it mean to solve the differential equation? What does that mean? Find y, right? Find the original function. That's what it means. So I'm going to have to integrate. Now, do you think that this has anything to do with this? We hope not, right? We hope not. I would rather, okay, let's pull out one of our, 2 integration rules. We can integrate separating the pluses. That's what we should do. Really wouldn't be, it wouldn't be helpful to add those together. So we're going to just integrate each piece. We're just going to integrate each piece. So let's do that. How is this integration going to work? What am I going to need to use here? U-substitution. And what about this one? Just the reverse power rule, right? So here, using a u-sub, what would I make u? Yep. U is going to be 1 plus x cubed. So du is going to be 3x squared dx. I don't have a 3 in here, so just for me, I would move the 3 out. 1/3 du equals x squared dx. And that's my u-substitution part. So now let's sub that in. All right. So I'm actually going to move the 9 out and the 3rd. So I'd have 9/3 on the outside, or 3. The x squared dx is going to be gone. It's going to be left with a du. And in the denominator, I'm going to have what's square root of u. And we just did one like that, didn't we? This guy right up here. Just like that. So let's finish it out. So that's going to be 3. Let's see, that's u to the negative 1/2. Add 1, get 1/2. So it's multiplying by 2, u to the 1/2 plus, let's do this one. I'm not putting a plus c yet. Don't let that bother you. Okay, I got to do this one. The integral of 5x is 5/2 x squared. Now I put the plus c. And that has also been bothering people all day long. I'll talk about that in just a second. Let me clean it up. Let's put the u back in. So y equals 6 square root of 1 plus x cubed plus 5/2 x squared plus c. That is my answer. Now let's talk about why I don't have a couple c's. My original problem, was it originally 2 problems? No. Why is it 2 problems? Because it's convenient for me, right? It's not because it's supposed to be 2 problems. It's 1 problem. So I should have 1 c. I shouldn't have multiple c's. Okay, we wouldn't put a c on each one and then make it a 2c. We wouldn't do that. It's just 1c because this is 1 problem. Alright, the only reason we made it 2 is for our convenience, not because that's what they were asking us to do. Okay, are we okay with that? Alright, excellent. Where are we? Here? We good?